deserve it, so it's fine.
And because we're recording this, it's not on camera.
Yeah. You know who you are. Okay, so we were still, oh wait, this is the wrong one. There we go. There's all the solution that we're going to work out. You guys don't want to see that. Eigenproblem for a 2x2 matrix. We're going to do an example in lecture 7-2. We are going to let the A matrix be the one given there, the 2x2 A matrix. We're going to find the eigenvalues and eigenvectors. This almost feels like something we don't need to do because, you know how to do it already, but it's probably good for a little refresher, don't you think? So 2x2 matrix, you should be able to do this by hand for like a 2x2, 3x3, 1x1. Don't forget that 1x1 matrix is a thing. I've given that on an exam before, thinking, oh, I'll give them this nice little softball. 1x1 matrix is almost trivial to find like the inverse of. It's the reciprocal, that kind of thing. And like people did not know what to do with a 1x1 matrix. And so 1x1, 2x2, 3x3. Be able to do eigenvalues and eigenvectors, please. Great. So eigenvalues, let's do that first. Eigenvalues. So we're going to use the formula from before, which was that the determinant of lambda I minus A has to be equal to 0. This is the condition that we have for lambda to be an eigenvalue, and so we can evaluate this determinant to find a scalar expression in terms of lambda that must be equal to 0, and that'll give us what our eigenvalues are. So let's go ahead and do that. So determinant of lambda I, so I is going to be a 2x2 identity matrix, right? Because A is a 2x2 matrix, needs to match those dimensions. And if we multiply an identity matrix by lambda, it's going to have lambdas along the diagonal and zeros elsewhere, minus A, which is 2, -4, -1, -1, equals 0. Okay, that's great. Let's do the subtraction step. Determinant of lambda minus 2, it's element-wise, right? 0 minus 4 is positive 4. 0 minus -1 is positive 1. Lambda minus -1 is lambda plus 1 equals 0. We can compute the determinant. We should know how to do the determinant of a 2x2, 3x3, 1x1. So we have lambda minus 2 times lambda plus 1. We have minus 4 times 1 equals 0. And we can simplify that down, expand out the products, and we get the expression lambda squared minus lambda minus 6 equals 0. And you guys have been solving quadratic equations for so long, I feel no need to walk us through that in detail. Lambda 1 and lambda 2 end up being 3 and -2. Cool. Any questions on how? Oh, and what are these? These are our eigenvalues. Bum-ba-da-bum. That was part of what was asked in the question. Sadly, that's not all I'm going to ask you in real questions in this class. This is just an exercise in eigenvalue finding, which is something that you should know how to do before coming into this class. Why are we even doing this lecture? I mean, seriously, gosh. I don't know. Friday afternoon lectures are weird. Always weird. Every time. we should definitely have snacks.
I feel like it's like that time of the day where it's like good.
Yeah. But sanctioned snacks only. Don't be bringing those special brownies.
Hey, I was saying pizza, so like legit pizza.
Yeah. Definitely not special brownies.
I think you're the only one.
So, okay, we've got our eigenvalues. What do they mean? What do they mean?
Yes.
What do they mean? What do our eigenvalues mean? So if this was our A matrix for our system, remember we found out that the eigenvalues are related to the roots of the characteristic equation, which governed the transient response and stability of the system, right? So these eigenvalues govern the stability of the system. Is this system stable? No. Don't ship this. If this was the analysis of the design that you came up with, don't ship it. You have an unstable eigenvalue, positive 3. The real part of one of your eigenvalues is positive. It's unstable. It's bad news. Okay. So that's good to know. You have an unstable eigenvalue. Means that probably this isn't the system you want to have at the end of the day, but it is what it is for now. And eigenvectors. So maybe. We'll see if we can do eigenvectors. Probably. We'll just do that. Eigenvectors, we'll use one of the formulas we came up with earlier in the lecture. So we'll use the equation that lambda I minus a times an eigenvector m. So we'll say this for a specific one. So lambda sub I and m sub I. So for some eigenvalue eigenvector pair, this should be the 0 vector. That just comes from the eigenproblem, or the definition of the eigenvalue eigenvector problem. So we'll use that and substitute each lambda I. Okay. So let's substitute first off lambda 1 equals 3. So notice something that could have happened up here. We could have gotten complex eigenvalues, right? We got real ones. Real ones are a little easier to work with, but the same exact procedure works if they're complex eigenvalues. No problem there. It's just that you got to do complex stuff. All of the things that you do here are complex, and the eigenvectors end up being complex. So that's like a thing to watch out for. Great. So lambda 1 equals 3. We can plug that into this formula, and in fact, I'm going to write it out in the general form, so just so that we have that in our minds. So lambda I, the A matrix we know, so let's go ahead and, so actually lambda I minus A we already computed up here, right? This is lambda I minus 2 for 1 lambda I plus 1 times the eigenvector. So this has components. I'll add a subscript. The first subscript will be the row and the vector it is. So m1i, and the second one will be m2i. So for eigenvector I, and this has to be equal to 0, 0. So for each lambda we plug in, we're going to get this problem. So I'll plug in lambda 1 equals 3. We're going to have 3 minus 2, 4, 1, 3 plus 1, m1, 1. We plugged in the lambda 1, so that's m1, and then m21 equals 0, 0. And this is simply 1, 4, 1, 4, m11, m21. Don't worry, we have not made a mistake. Why did I say though? What do you think? These rows, or equivalently columns, are not linearly independent, are they? How do I know that? Because linear algebra told me. You got to have, if you're going to have a unique solution to a set of equations, you need to have linearly independent rows, linearly independent equations. We don't have that. And this is going to happen every single time when we find an eigenvector. So this is not something that, like, oh, no, we messed up somewhere and should freak us out. We know this is coming. It's going to be this way every time. What we have is a system that has an infinite number of solutions, okay? Because it's only constrained by one equation, but there are two unknowns. So there are many ways we could go about solving for what that family of solutions is. I'll teach you guys the way that I think is maybe the most, or maybe the easiest way to go with it, but you can choose your own way if you have a preferred way. So what I'll do is I will write, so you can take either equation, they're equivalent, right? So the first row gives us one equation and it's equivalent to the other equation. So in this case, it's identical to the other equation. It could also be any scaling of the original equation too. So you can do, like, even if you multiply the first row by 10, 10 times m11 plus 40 times m21 equals 0 is the same equation. So it doesn't matter which one you do. So we've got 1 times, well, instead of m11, I'm going to choose something for m11. I'm going to say m11 is just equal to 1. Okay? I'm artificially constraining it. We're going to find out what the solution for m21 is when m11 is 1, and then we're going to use some knowledge we have to extrapolate from that solution. So I'm going to say m11 is 1. And then I'm going to say 4 times m21. We're going to solve for what m21 should be. And that should be equal to 0. If you solve this equation, you get that m21 should be equal to negative 1/4, right? And that means that our m1 vector is equal to, I'm going to leave a little bit of space out here before the vector, and we said that m11 was 1, m21 was negative 1/4. So traditionally, the eigenvector is just given as one vector, just one solution, any solution, pick a solution. As long as it's a solution, you're good. So that's why you can arbitrarily just pick m11 and solve for what m21 has to be. However, also valid is any scaling of this, any scaling by a real number. So I'm just putting alpha in there to remind us that we could choose this first one to be 4, for instance, like just to pick one arbitrarily, and then this one down here would have to be scaled by 4 as well, so it would be negative 4/4 or negative 1. That's also an eigenvector. Any scaling of an eigenvector is also an eigenvector. Okay? So the eigenvector is really only unique in the direction that it's pointing. Its magnitude is not unique. Okay, so we found m1, and now let's plug in lambda 2 equals negative 2. And this one, we're going to plug in this formula again. So lambda 2 is negative 2. So it's negative 2 minus 2, which is negative 4. 4, 1, negative 2 plus 1 is negative 1. M1, 2, M2, 2 equals 0, 0. Okay, once again, we can read off either equation. Let's take the upper equation for the hell of it, but we can take the lower equation. It'll give us the same solution, so no big deal. So we can do negative 4 times M12, which we're going to set to 1 again. I just always usually set the first one to 1 and see what everything else has to be from that. And 4 times M22, so plus 4 times M22 must equal 0. And we see immediately that M22 must just be equal to 1. Right? So, therefore, M2 is equal to, we assumed that M12 was 1 when we plugged it in right here. And we solved for M22, which was also 1. And I should probably put in this scaling. Any scaling of this is also valid. So if you had chosen M12 to be 7, then M22 would need to be 7 as well. So I will put in this scaling factor, beta, any real number, for that one. So those are our eigenvectors. And that was that. Any questions?
Why, sort of, we're going to use complex numbers in this particular class?
We are.
Is it like associated with sort of electronics, or what is the relationship between complex numbers and what are we doing?
So you may recall that when we were looking at our I think that maybe just hearkening back to the homogeneous solutions and the characteristic equations that we would find. So characteristic equations. They always had this form of, we used actually lambda in these characteristic equations, right? We had like lambda cubed plus 5 lambda squared plus 2 lambda plus 7 equals 0. This was part of the solution technique that we developed for input-output ODEs, right? And the roots of this were sometimes complex.
Is that because when we solve for it, we get a root of a negative number?
Exactly. So that would happen sometimes. These roots would come out to be complex. And we talked about that specifically in the last chapter when we discussed second-order system responses. And we saw, okay, lambdas show up in complex conjugate pairs sometimes. And essentially that means that there is a negative sign under the square root in the quadratic formula, which can arise. And if that does happen, then there are a lot of characteristics of the system that we can understand. So we went through them to an extent, like, okay, if you have complex roots and your damping ratio is between 0 and 1, then you have an underdamped system, for instance. And you have the oscillation that occurs in the free response. So those lambdas coming out complex are really telling you how the system's going to respond. If those lambdas come out with negative real parts, it's stable. If they come out with positive real parts, it's unstable. And in between, it's marginally stable. It's just 0 real part, purely imaginary numbers. So the lambdas being complex is something we've actually seen several times before in the context of the characteristic equations. So now, in the last lecture, we identified that eigenvalues, values, are equivalent to roots of the characteristic equation. And that was the box that we had, the green box, characteristic equations. So everything that we knew about roots of characteristic equations, we can map onto our understanding of eigenvalues now. And so when we have eigenvalues that come out complex sometimes, it's totally valid. It just means that when we find the solution, we're going to have oscillations that will occur, which is kind of like the defining aspect of having any imaginary aspect to your roots of your characteristic equation or your eigenvalues. And in this context, it means that the M11, M21, M12, M22, these eigenvector components are going to show up in that case as being complex as well. All of what we've done here can be done with complex numbers too. It's just a little bit more tedious because you have twice as much number going around with you, right? It's 2 parts to each number. So it's a bit of a pain when they're complex. I think that in the homework you do a 2x2. You might do up to a 3x3 with complex. That's a little bit more tedious than maybe I want us to do. In the next lecture, I'll do a little example. Actually, no, it's this. It's next lecture. I'll do an example with complex roots, I think. Is it going to have complex roots? Has negative numbers, but they look like they're real. That's the next lecture, 7.4. In lecture 7.4, there are going to be complex roots. So we'll look at that. It's a little easier to use MATLAB or something to find the roots in that case, though, than to do it by hand. But it's good to be able to do that for, like, realistically, probably like a 2x2 or a 1x1 is what I would give you if there were going to be. Well, 1x1, it never shows up, actually.
I was just wondering what's the difference in like using complex or real. Seems like they're sort of the same in the same terms of not the damping, but not really sure at this point.
Yeah, I mean, I would encourage you to go back and look at the it's like, I think it's chapter 6, lecture 3, I'm pretty sure. When we talk about second order systems, because those second order systems have that complex possibility to the roots, and so we talk about it. I mean, we could talk about it more, but to some extent we talk about it in that lecture, and we discuss what happens when you have lambdas showing up in with imaginary parts associated with them. And what it does is it adds this oscillation to the response. So you don't not only have these exponential envelopes, but now you have also oscillation happening. So that's what the imaginary component kind of always signifies for us. It's one of the things that it signifies for us. Okay, great.